Lesson 13, calculating and comparing square roots. Today we begin by learning about our new concepts, and that would be what we would call a perfect square. These blue highlighted terms are going to be our vocabulary terms. It's going to be important for us to get to know right off the bat today. A perfect square is a number that is a square of an integer, which is the product of an integer, and itself is a perfect square. So you take a number and you multiply it by itself. Here's the example, 2 times 2. 2 times 2 gives you a total of 4. 4 would be an example of a perfect square. 3 times 3, or 3 squared. 3 times 3 is 9. 9 would be an example of a perfect square. A square root is indicated by a radical symbol. Here's our radical symbol. And a radicand is the number or the expression under a radical symbol. So here you've got square root of 50. 50 is what's called the radicand. So we identify what that number is called with the radical symbol, and then 50 is the radicand. In this example, 2 times the square root of 7. 7 is the radicand because it's underneath this radical symbol. A square root of x, written square root of x, is the number whose square is x. For example, 4 squared, so 4 times 4 equals 16. The square root of 16 is 4. Notice these are opposites of each other. Like addition and subtraction are opposites of each other, and multiplication and division are inverse operations of each other. A square root and a square of an exponent are opposites of each other or inverses of each other as well. We're going to learn today in terms of calculating square roots. Where you take the square root of a number, you're thinking what times what equals this number, which if you know your perfect squares, you then have that calculation. 4 times 4 equals 16. When I take the square root of 16, I'm only looking for one digit as the answer. A square number can only end with the digits 0, 1, 4, 5, 6, and 9. However, not all numbers ending in these digits will be perfect squares. Let's take a look at what those perfect squares are. So we have those listed in our brain, and we can work on memorizing those so that it just becomes easier and easier and easier. Remember, a perfect square is a number that's multiplied by itself, and that solution gives us what would be the perfect square. An integer multiplied by itself or an integer squared gives us that answer. I'm going to go through the list numbers 1 through 20, and I want you to, if you need to, rewatch this and rewatch this and rewatch this until all of these digits, all these numbers get listed in your brain so we can easily come up with what our perfect square is, and then easily solve square root problems, which would be the inverse of each of these solutions. Let's take a look. 1 times 1, 1. 2 squared, 2 times 2 is 4. 3 squared, 3 times 3 is 9. 4 squared, 4 times 4 is 16. 5 squared, 5 times 5 is 25. 6 squared, 6 times 6 is 36. 7 squared, 7 times 7 is 49. 8 squared, 8 times 8 fell on the floor, up pop number 64. 9 squared, 9 times 9 is 81. And 10 squared, 10 times 10 is 100. Now you probably learned those in your math facts and probably have known those for a really long time, but here's where we're going to take that to the next level and turn this into our new learning. So we've got 11 through 20. We're going to square each of those numbers, which means again you're multiplying that number by itself. 11 squared is 11 times 11. We've got 121. 12 squared, 12 times 12 is 144. 13 squared, 13 times 13 is 169. 14 squared, 14 times 14 is 196. 15 squared, 15 times 15 is 225. 16 squared, 16 times 16 is 256. 17 squared, 17 times 17 is 289. 18 squared, 18 times 18 is 324. 19 squared, 19 times 19 is 361. 20 squared, 20 times 20 is 400. Feel free to watch this again to help you remember each of those terms as our perfect squares. Now, as we're turning perfect squares into how we would figure out and calculate square roots, we got to understand that the opposite operation, the inverse operation of squaring something to create a perfect square, is our square root. If I would take and square root every single one of these numbers, for example, square root of 400 equals 20. Square root of 361 equals 19. Square root of 324 equals 18. And you would see that pattern continue. Square root 17, square root 16, square root 15, square root 14. If I had that radical symbol drawn there, all of these numbers become my radicands, and what they were squared initially, after they're square rooted, becomes that same number again. So they're inverse operations. Back to our example problems in lesson 13. In example 1, it asks you to find square roots of perfect squares. Now if you use that list that we just covered to calculate perfect squares, you'll know that when you're given a question about a square root, if it's a perfect square or not, if it falls into that list, if it's one of our integers, numbers 1 through 20, multiplied by itself to give us those solutions that you just learned, if it's not one of those, then it's not considered a perfect square. For example, letter A, is the radicand, the square root of 50, a perfect square? Well, was 50 on our list? 50 is not a perfect square. It was not multiplied as 6 times 6 is 36, 7 times 7 is 49, so 50 is close, but it's not there. 8 times 8 is 64. It missed the mark. It's not a perfect square. Letter B, is the radicand square root of 64 a perfect square? 8 times 8 fell on the floor, up popped number 64. Square root of 64 is a perfect square. That would be 8. In example 2, it says not all numbers are perfect squares, but square roots can help us to estimate where these numbers lie. In that first example, we said square root of 50 is not a perfect square. So we're going to use what we know as perfect squares to estimate what number this falls between. It says estimate the value of the square root of 50 to the nearest integer. Explain your reasoning. Well, 50 is not a perfect square, so I'm going to think about what numbers that are multiplied together would get me close to 50. 6 times 6 is 36. 7 times 7 is 49. That's close to 50. And then 8 times 8 is 64. So 50 falls actually between 49 and 64. So it falls between what would be the square root of those two digits. To determine which two perfect squares 50 falls between on the number line, you have to calculate those squares. So 49 and 64. The square root of 49 is 7 and the square root of 64 is 8. So we would say that the square root of 50 falls between 7 and 8. Right here. 50 is between the numbers 7 and 8 because square root of 49 is 7 and the square root of 64 is 8. So 50 is closer to 7, so we can make that approximation or that estimate that it's right here. Basically, you're trying to find two solutions, answer that is smaller than and an answer that is larger than, where that number falls between. When comparing expressions that contain radicals, simplify the expressions with radicals first. Next, perform any operations necessary, then compare the expressions. In example 3, we're comparing expressions, which means we're using our order of operations to solve the left-hand side and then the right-hand side of this expression. When you have a radical symbol, that's kind of like when you have an exponent, so it becomes one of the very first things that you're going to do in your order of operations. So here's our problem, square root of 4 plus square root of 36 in comparison to square root of 9 plus the square root of 25. Well, let's go through and find our solutions to these square roots. Square root of 4, perfect square is 2. Square root of 36 is 6. 2 plus 6 is 8. Square root of 9, perfect square is 3. Square root of 25, perfect square is 5. 3 plus 5 is 8. They are the same, so you would say that those two things are equal. In example 4, we're applying this scenario with square roots to our skill of area. Remember, area is length times width, and when we have something that is a square, it works out really well to use the math application of square roots because square root or an exponent, a square of something, is multiplying that number by itself. The area of a dance floor that is in the shape of a square is 289 square feet. What is the side length of the dance floor? Explain. Side length can be found by finding the square root of the area. Because it's a square, both of the sides are the exact same length. That means to find the area of that, you would multiply those two things together. So we take the total area, 289, and you've got that equaling your square footage. You take the square root of that number, and you find 17. Square root of 289 from our perfect squares is 17. Next, let's take a look at our lesson practice problems. In lesson 13 practice problems, we're going to apply what we've learned in the 4 different example problems from lesson 13 today. Here it asks us to calculate the square root of 225. If I remember back to my perfect squares, something times something equals 225. 15 times 15. So the square root of 225 equals 15. Remember, when I'm thinking about perfect squares, I'm thinking about what numbers multiplied together by themselves equal a digit. And I take the square root of that, it gives me that number that's considered a perfect square. For letter B, we've got the square root of 350. Is 350 one of those numbers that falls into our square roots? No. Restart. Practice problems for lesson 13. In letters A and B, it's asking us if the radicand, that's the number underneath our radical symbol here, are perfect squares. In letter C, it asks us to estimate, and in letter D, it asks us to compare. Letter E, it's going to apply our understanding of square roots in a word problem. All these come right from the example problems that we learned in our lesson today. Let's get started. In letters A and B, it's asking us if these numbers are a perfect square. If you have to go back in the video and watch where Mr. Shane listed all those perfect squares, numbers 1 through 20, it might be helpful. Otherwise, we want to get those things ingrained in our brain so that we can automatically see a number and say, is that a perfect square from those multiples that we know. If I look at letter A, square root of 225, I think back, what numbers multiplied together give me 225? 15 times 15 is 225. Therefore, this is a perfect square. We would say yes, because 15 squared equals 225. The square root of 225 is then 15. Those are inverse of each other. In letter B, you've got the square root of 350. Now, 20 times 20 was 400, and let's see, 19 times 19 was 361, 18 times 18 was 324. We didn't have any of those that hit 350. So this is not a perfect square because it does not fall into one of those exact integers being multiplied by itself. Letter C says estimate. Whenever we don't have a perfect square, that doesn't mean we can't solve a problem with square roots. See, we have to think about where this number is on our number line, and then we have to think about the numbers that would be close to it in terms of perfect squares that we do know. Now, 37 is really close to one of the perfect squares. 6 times 6 is 36, so the square root of 36 is 6. That's one of the numbers that it's really close to. If I show that on a number line, 6 times 6 is the square root of 36, so that's right here. Well, the square root of 37 must be really close to that. Therefore, it's going to be estimated to be right around that point. We want to think about the number that's smaller than, right here. 6 times 6 would be 36, or the square root of 36 would be 6. That's really close. And a number that's bigger than, to find out where this number falls in between. Well, the next number in our squares, 6 times 6 is 36. 7 times 7 is 49. The square root of 49 would be down here on the number line. This number falls between 6 and 7. In letter D, it asks us to compare using our knowledge of perfect squares. Here we have square root of 16 plus the square root of 441. Square root of 441 is actually 21. It goes a little bit beyond what we learned today. Square root of 16 is 4. 21 plus 4 is 25. Let's compare that to this right-hand side. Square root of 361 is 19. And the square root of 81 is 9. 9 plus 19. That's 28. Our answer here would indicate that we would eat the larger number. Alligator eats a larger number. So this side, 28 is greater than. 25 is less than. 28, 28 is greater than 25. In letter E, it asks us to find the area of a sandbox that the city park is installing. The area of the sandbox is 169 square feet. How would we find the area? If I have a square, I know that both of those side lengths are exactly the same. To calculate that, I take the square root of 169, I take the square root of the area, and I'm going to find out that this is actually 13 times 13. It's a perfect square. 13 times 13 equals 169. The square root of 169 is 13. So the side length would be 13 feet on both of those sides. Because it's a square, it becomes a perfect square in this scenario. Hopefully that helps. Good luck with your assignment.